right here on Earth, that incredible energy source, nuclear fusion, it's tantalized scientists for decades.
Absolutely.
Today we're going deep into why making that happen is just, well, unbelievably hard.
Exactly. And we've got some great material here, this pasted text, which really lays out the fundamental obstacles, the things we really need to get past, including some pretty fascinating physics like the Pauli exclusion principle.
Okay, so listener, your mission with us today is to get a real handle on the core scientific reasons. Why fusion is so difficult despite, its jaw-dropping potential. We're not getting lost in the engineering side today. We're demystifying the basic science. Okay, so let's unpack this. What's the absolute first, most basic wall we run into?
Well, the text points straight to the Coulomb barrier. At its heart, it's about electrical repulsion.
Right.
The nuclei of atoms, the things we want to actually fuse together, they carry a positive charge because of their protons. And, well, as we all know from playing with magnets, like, charges just really don't want to get close.
Right. It's like trying to slam two north ends of magnets together. You can push, but there's this sort of invisible force pushing back.
Exactly.
Now, the source emphasizes that this pushback isn't constant, right? It gets way, way stronger the closer these nuclei get.
That's a crucial point. It escalates rapidly as the distance shrinks. So as we try to force these positively charged nuclei together, the resistance just becomes, well, exponentially greater.
So the first takeaway is simply getting these positively charged particles near each other takes immense energy just to fight that natural repulsion.
A tremendous amount of energy. We're talking about needing conditions that can overcome that fundamental force just to get them in the same vicinity.
It's like trying to sprint up an infinitely steep hill just to get to the fusion starting line. But it's not just that electrical resistance we're battling, is it? The paper also mentions the Pauli exclusion principle.
Ah, yes.
That sounds like we're dipping our toes into the wonderfully weird world of quantum mechanics.
We are indeed. So while the Coulomb barrier is, rooted in classical physics, electricity and magnetism, the Pauli exclusion principle takes us into the quantum realm.
Okay.
And it applies specifically to a category of particles called fermions. Now, this includes protons and neutrons, the basic building blocks of nuclei, sometimes called nucleons.
Okay, so fermions, protons, neutrons. In simple terms, what does this principle actually tell us about them?
Basically, it states that no two identical fermions can occupy the exact same quantum state at the same time.
The same state. What does that mean exactly?
Think of a quantum state as a unique kind of address for each particle. It includes its location, its energy, its spin, things like that.
Okay.
So if you try to cram two identical protons, for instance, into the exact same tiny space with the exact same spin, well, the principle says, nope, can't happen.
Like trying to park two identical cars in the same parking spot at the same time?
That's a good analogy, yeah. It's physically impossible according to quantum rules. So even at that tiny level, there's a limit to how tightly you can pack identical particles.
So when we're trying to force these nuclei together for fusion, are we bumping up against this Pauli repulsion too? On top of the Coulomb thing?
Yes, at extremely short distances. When identical nucleons, say two protons from different nuclei, start to overlap significantly, this principle manifests as another repulsive force.
Wow.
It's like they're saying, hey, this quantum state, this little spot, it's already taken. So it adds another layer of difficulty right when you think you're getting close.
The universe really doesn't want to make it easy for us, does it?
Not when it comes to fusion, apparently.
But here's where it gets really interesting. Nature does manage this. Stars pull off fusion constantly.
Millions of years.
And we're trying to mimic that. So how do stars, and potentially, how do we overcome this double whammy of repulsion, Coulomb, and Pauli?
Well, the source material highlights a couple of key mechanisms. The first one is just incredibly high thermal kinetic energy.
Meaning heat. Like a lot of heat.
A lot of heat.
Yeah.
The cores of stars and the fusion experiments we're building reach temperatures that are just astronomical. Tens to hundreds of millions of degrees Kelvin.
Okay.
At those extreme temperatures, the nuclei are moving at absolutely breakneck speeds, just whizzing around.
So it's like giving our repelling magnets, our nuclei, a super powerful throw, hoping their sheer speed smashes through that repulsion.
That's a useful way to think about it, yeah. This huge kinetic energy allows the small fraction of the nuclei to collide with enough force that they can get significantly closer, pushing against that Coulomb barrier.
Partially overcoming it.
Partially, yes. But here's the thing. Even with these mind-boggling temperatures, the average energy often isn't quite enough to completely bulldoze through that barrier in a purely classical sense.
Ah, so brute force isn't the entire solution then, there's still a gap.
There's often still a gap.
That must be where this quantum mechanical tunneling comes in, which honestly sounds like something straight out of a sci-fi movie.
It does sound a bit fantastical, doesn't it? But it's a very real, very fundamental part of quantum mechanics.
Okay, explain tunneling. How does that work?
Well, because particles at the quantum level also behave like waves. It's weird, but they do.
Wave-particle duality, right.
Exactly.
Yeah.
Because of that wave nature, they have a non-zero probability, a chance of just passing through an energy barrier,
Yeah.
even if they don't technically have enough energy to go over the top.
Wait a minute, hold on. So even if they don't have enough energy to climb the mountain, there's a chance they can just, appear on the other side?
Essentially, yes. They can tunnel through the barrier.
That's wild, like finding a secret passage through the energy mountain instead of having to climb over the peak.
That's a great analogy. And the probability of this tunneling happening depends on things like the height and the width of that barrier.
Okay.
So when nuclei have higher kinetic energy, they can get closer before being repelled. This effectively makes the remaining Coulomb barrier narrower.
Ah, making the tunnel shorter.
Exactly, which significantly increases the likelihood of tunneling occurring. This quantum tunneling is absolutely critical for fusion, especially in stars where temperatures, relatively speaking, might not always be high enough for purely classical collisions to do the job.
That's just mind-bending. So it's not just about smashing them together really, really hard. There's a significant element of, quantum luck involved.
You could call it probability, yeah, but it's a well-defined quantum probability. And it's the crucial pathway that allows fusion to happen at the rates we actually see in stars. The heat boosts the chances, makes tunneling much more likely for those high-energy particles.
Okay. So we've used incredible heat, got the particles moving super fast, and then employed some quantum trickery tunneling to get these nuclei within spitting distance past the main barriers.
Past the main Coulomb repulsion.
What happens then when they finally get close enough to almost touch? That's where the strong nuclear force finally comes in, doesn't it?
Precisely. That's the final piece of the puzzle. Once the nuclei manage to get incredibly close, either by tunneling or just having enough energy, we're talking within a range of about 1 to 2 femtometers.
Which is ridiculously tiny, right? Like smaller than the nucleus itself.
Way smaller than an atom, yes, within the scale of the nucleus itself. At that point, the strong nuclear force takes over.
The strong force,
Yeah.
aptly named, I assume.
Extremely. It's one of the 4 fundamental forces of nature, and it's unbelievably powerful. But, and this is key, it only operates over these extremely short distances.
So it's like a super powerful short-range glue. It only works if you get the pieces practically touching.
That's a perfect analogy. And this strong force is attractive between the nucleons, the protons, and neutrons. At these tiny distances, it just completely overwhelms the electromagnetic repulsion, the Coulomb force.
It just grabs them.
It grabs them and binds them together into a new, heavier nucleus. That binding process is what releases the tremendous amount of energy we associate with fusion. That's the EMC2 part.
Wow. And this strong force, once it kicks in at that range, it's powerful enough to overcome everything else, the leftover Coulomb repulsion, even that Pauli repulsion we talked about.
That's absolutely correct. At those incredibly short distances, the strong force is king. It dominates, overrides the repulsive forces, lets the fusion reaction complete, and releases that massive burst of energy. It's the final critical step.
Okay, let's try and recap this. We face this huge initial wall, electrical repulsion, Coulomb barrier.
Yep, like charges repel.
Then, at really close range, there's this quantum issue, the Pauli principle, adding another layer of pushback for identical particles.
Can't occupy the same state.
So we fight this by heating things up to insane temperature,
Millions of degrees.
giving the particles enormous speed. This helps them get closer and dramatically increases the chances of this quantum tunneling effect,
The sneaky shortcut.
allowing them to pop through the remaining barrier. And then, only when they're incredibly close, this super strong, short-range nuclear force takes over, glues them together, and releases all that energy.
That's a wonderfully clear summary. And what's fascinating, really, is that making fusion happen isn't about finding ways to ignore these fundamental physics principles.
Yeah.
It's about creating the incredibly extreme conditions where these principles interact in just the right way for fusion to win out.
And for you, our listener, who wanted to quickly but thoroughly get a handle on why fusion is such a massive challenge, I think this paints a much clearer picture, right? It's about these fundamental scientific hurdles.
Mm,
It's not just engineering bigger magnets, it's wrestling with the very fabric of physics at its most basic level. So basically, the universe doesn't want us messing with its sun-making recipe without a serious effort.
precisely. Understanding these barriers, the Coulomb repulsion, the Pauli principle, and the ways that nature and hopefully us can overcome them with heat and quantum tunneling, letting the strong force do its job.
Yeah.
Well, it's essential, not just for fusion energy research, but for understanding how stars themselves work.
Right, how the cosmos is powered.
Exactly.
So we've explored how this incredibly powerful energy source hinges on this complex dance between forces and quantum probabilities. Knowing these immense hurdles, it really makes you think, doesn't it, about the future of energy. Can humanity really replicate the power of a star here on Earth now that we better understand the fundamental scientific gauntlet we need to run? It's definitely something profound to ponder.